got Breakfast of Champions going here. I had all kinds of plans for making some food in between classes and stuff, and I ended up with a bag of chips and a Coke. So, hey, you know.
I had the same plan, but I ended up doing physics homework instead.
Oh, yeah, that's almost the same as eating chips and drinking a Coke.
It's nice to know that the from the chips bags on your beer desk is still valid in this day and age.
Oh yeah, totally. All right, let's see. We were talking about induction last class, and I posted a new homework assignment, and it's just some induction proofs, and these are proofs from the second textbook that's listed on Canvas, and it's from chapter 3, I think, of that text. So you can eyeball those and ask questions, but that'll be due a week from today, so we basically just skipped a week of homework around the exam. So we're gonna keep working on induction questions and looking at proofs and looking at some details of that. Any questions before we jump into all of that? All right, so you get mostly a side view of me while we're doing these. And again, the goal with these different things that we're going to be working on is mostly to try to keep building our intuition for how an inductive proof works, to try to keep getting our familiarity with the mechanics of an induction proof and so on. And so sometimes these will be extremely rigorous, sometimes they'll be extremely hand-wavy, sometimes something in between. But the goal is always to understand this idea of how a base case and an inductive step can be shown and then used to prove something typically much more powerful. All right, so let's start with an inequality. Let's prove that n is smaller than 2 to the n for all n bigger than or equal to 1. And we can probably assert this by saying, if we multiply 2 a bunch of times, eventually it's got to be bigger than something and so on. But let's forget what we know for the most part about inequalities and about exponential growth and so on, and let's just prove this by proving a family of propositions. So I'm going to start off with P of n as the proposition that n is smaller than 2 to the n. And just and sidebar to note here, I would not want to say P of n is the proposition that n is less than 2 to the n for all n bigger than or equal to 1. That doesn't make sense, right? P of 5 would be the proposition that 5 is less than 32 for all 5 bigger than or equal to 1. That's kind of nonsensical. So P of n is just this proposition. It's the proposition that n is less than 2 to the n. What we're trying to show ultimately is that every P of n is true, so we're trying to prove P of n for all n bigger than or equal to 1. But each P of n is just a single statement. P of 1 is the proposition that 1 is less than 2. P of 5 is the proposition that 5 is less than 32, and so on. Alright, so first step is the base case. P of 1 says 1 is less than 2, and this is true, because we know that about 1 and 2. So in this case, that's all there is to establishing the base case. Just write out what P of 1 is. It says 1 is less than 2 to the 1, which is 2. And since we know 1 is less than 2, P of 1 is true. So the inductive step. Here we need to prove P of n implies P of n plus 1 where n is some number bigger than or equal to 1. So start off with our hypothesis, P of n. That's the hypothesis or premise. Let's write out what P of n says. Since we're stating P of n is true, this means n is less than 2 to the n. That's the definition of P of n. And we want to do something so that eventually we have proven P of n plus 1. So ignore this. We want to prove P of n plus 1, which means we want to prove n plus 1 is less than 2 to the n plus 1. That's our goal. If we can prove that, then we can tie all of this up in a nice little package and say, by mathematical induction, we're done. And the only thing we know so far is that n is less than 2 to the n. So we want to get from here to there. And to me, the idea is, you know, when I go from here to here, I'm increasing this left side by 1. That's a really small amount. When I go from here to here, I'm doubling the right side. That's a big increase. If I can show that this increase is bigger than 1, I can use this to assert that. And so here's one way to do this. I can note that 2 to the n plus 1 is equal to 2 times 2 to the n, which is 2 to the n plus 2 to the n. So this side looks like this plus 2 to the n, whereas this side looks like this plus 1. And I'm going to assume my teacher will let me assume that 1 is less than 2 to the n, because 2 to the n is always positive, and if n is at least 1, this is at least 2. So I'm going to do the following, and again, this could be considered hand-wavy. If this was a math course, we might need to actually show this. But 1 is less than 2 to the n, you know, that's just the way it is. I don't know what a good reason would be. But if 1 is less than 2 to the n, then I can say the following: n plus 1 is less than 2 to the n plus 2 to the n. That's properties of inequalities. So if a is less than b, a plus x is less than b plus x. Right? Inequalities are preserved when you add to both sides, or if you multiply both sides by something positive. And now I'm just going to replace 2 to the n plus 2 to the n with 2 to the n plus 1, and that's, you know, exponents. This is equal to that. And now this is the statement of P of n plus 1. That's the definition of P of n plus 1. And so P of n implies P of n plus 1. And I always run out of space at the bottom of these proofs for some reason. So therefore, P of n for all n bigger than or equal to 1. That's mathematical induction. That's what we were trying to show. So the usual structure that we keep seeing, we state the hypothesis, we write it out, and then we do something, and that something changes from proof to proof, but we do something that eventually gets us to where we can basically write P of n plus 1. In this case, the something was noting that 1 was less than 2n, and so adding these things to both sides and preserving the inequality, and then observing this is P of n plus 1, so that implies that, and then you're done using mathematical induction. All right, so that's an example with a certain degree of rigor that can tangle us up sometimes, right? We can get caught in all of the symbology and stuff. Let me show you a much more hand-wavy proof that we can do just to convince ourselves of something that we've been using already, which is the size of the power set of x is equal to 2 raised to the size of x, where x is a finite set. In other words, if you have a set with 5 elements, the power set will contain 32 subsets. 32 elements, which are each subsets of your original set. So we asserted this in the beginning of the course, and we've seen a few versions of this. Let's actually prove it. Yeah, go ahead and send me an attendance note. I think most people are here who are coming. Alright, so as usual, start with a family of propositions. And this one's less obvious. We want to bless you. We want to make a family of propositions, and we want to assert this entire family is true. But I don't have an n here, right? So what could we use for a family of propositions in order to prove that this is true for all finite sets x? In other words, what could we try to induct on? What variable or what property? Any guesses, ideas?
Can we like pick a variable to be the value, like the cardinality of x?
Ah, exactly. We could induct on the cardinality or the size of the set, right? Because we're trying to show this is true for all sets. Well, that's a huge collection of things, right? But all finite sets, and that's a clue. And we know that a finite set always has 0 or more things in it, and it's always an integer, right? And so yeah, we could induct on the size of the set. So let P of n be the proposition. Cardinality of the power set of x equals 2 to the cardinality of x for any set x with cardinality equal to n. So P of 1 will be the proposition that any set with a single element satisfies this equality. P of 2 will be the proposition that any set with 2 elements satisfies this equality. P of 1,000,000, any set with 1,000,000 elements satisfies this. And to show that this is true for all finite sets, we're going to say let's prove P of n for all n bigger than or equal to, I'll just go with 1. We'll stay away from the empty set. Not that we have to, but why make things weirder? So we'll just prove P of n for n bigger than or equal to 1. So we'll prove this for any set with at least one element. And then we can also see it's true for the empty set. Alright, so let's think about a base case. P of 1 says the size of the power set of x is equal to 2 to the number of things in x, where x is a set containing a single element. Well, if the cardinality of x is equal to 1, this means the number of things in the power set of x should be equal to exactly 2. In other words, the base case says any set containing a single element, the power set has 2 elements. Well, if we have a singleton set, it contains one element, we can write out all the subsets, and it's going to be either the empty set or the set itself. And we know those are the only subsets, regardless of what this element is. Right? The only subsets are the trivial subsets, the entire set or the empty set. And the cardinality of this is equal to 2. So P of 1 is easy to confirm. I think P of 0 would actually be easier, but I don't want to get into the weird stuff. But proving the base case, pretty straightforward. So let's look at the inductive step. Prove P of n implies P of n plus 1, where n is bigger than or equal to 1. Alright, so this is where we're going to get pretty hand wavy. That's okay though. So let's prove P of n plus 1. So I'm going to assume P of n. That's a hypothesis, which means the number of things in the power set of x is equal to 2 to the n, where whenever x is a set containing n elements. Alright, P of n says, if we have a set containing n elements, the number of things in the power set is 2 to the number of elements, n. So if x contains n elements, the number of subsets of x is 2 to the n. We're taking that as our hypothesis. Alright, so let B for big be any set containing n plus 1 elements. So the cardinality of big is equal to n plus 1. And we want to explore the power set. Alright, so here's where we do something that's a little weird. We know n is bigger than or equal to 1. We know that B contains n plus 1 elements, so it contains at least 2 elements. Okay? Pick any one element. Let me call it A for any one. Pick any one element of B. Right, B is this big set, it's got n plus 1 things. I'm just going to choose one element. I'm going to call it A. Alright, any subset of B either contains A or does not contain A. Right, A is one element I'm picking from this set B. If I pick any subset of B, there's two possibilities. It contains A or it doesn't contain A. So here's the question. If a subset of B does not contain A, it's also a subset of this thing, B with A removed. Right? A subset of B that does not contain A, sorry, I should put that down here. A subset of B that does not contain A is a subset of this set. Right? Because this is B with A removed. And the cardinality of this set is n. B contains n plus 1 things. If I throw away A, this set contains n things. So how many subsets are there of this slightly reduced set? Well, since this contains n things and we know P of n is true, the number of subsets of this is 2 to the n. So the number of subsets of B that do not contain A is 2 to the n. On the other hand, if we have a subset of B that contains A, that's a subset of this set with an extra A tossed in. And so how many subsets of this set are there? 2 to the n, that's P of n. And if we take each of those subsets and we add A to it, we get all the possible subsets of B containing A. So there's a total of 2 to the n of these subsets. And since every subset is either one of these or one of these, the total number of subsets of B is 2 to the n plus 2 to the n, which is 2 to the n plus 1. And so that's the number of things in the power set of B. And so we've shown by some waving of our hands that for any set containing n plus 1 elements, the number of subsets is 2 to the n plus 1. That's P of n plus 1. And so that's a hand-wavy proof that P of n implies P of n plus 1, and therefore P of n is true for all n bigger than or equal to 1, and the reason is mathematical induction.
My brain hurts.
That's good. That means you're thinking about it. So let's suppose.
The way,
Yeah.
the way that was explained in the other one doesn't make as much sense as because I was thinking just like, oh, you can just say that by adding a, you then double the possible amount of subsets.
Mm-hmm.
Which makes a bit more sense than what this says. Because how do we prove that that 2 to the n will be either contains a? How do we prove that the set power set's 2 to the n with that case? Because I understand with the other one it's like, oh, without. But then we're just saying, oh, we're adding a or something like that.
So let's look at an example. So let's assume P of 4 is true, and let's prove P of 5. So suppose B is equal to, I don't know, 1, 2, 3, 4, 5. It's a set containing 5 elements, right? And let's start listing the subsets of B, right? So subsets of B. Well, 1, 2, 3, 4, 5. I'm not going to list all 32 of them. Right? There's a whole bunch of subsets. And let's suppose that I'm picking out this one element A, right? So if I pick any particular subset and it doesn't include the number 1, right? It's a subset of this. So some of these subsets will be subsets of this thing. And I've got 2 to the 4th, which is 16 of those subsets. But if I pick a subset that includes a 1, like, 1, 2, 4, I can write that as the set containing 1 union the set containing the other elements. And this is a subset of this thing. So for every subset of this, I can throw a 1 into it and get a subset of B. And for every subset of B containing 1, I can ignore that 1 and get a subset of this. Let me do a simpler set. Let's just think about a set of 3 elements. So the possible subsets are B, C, A, B, A, C, A, B, C, and the empty set. So there's our 8 subsets. this set is this set with an A added. And this set is this set with the A removed. This set is that set with an A added. And if we remove the A from here, we get that. This set corresponds to this set. This set corresponds to this set. So we can take all the subsets of this and split it into two groups. The first group is the set of subsets that don't contain A. The second is the set of subsets that do contain A. And there's this one-to-one correspondence, right, between things in the first group and things in the second group. And so we know the size of this is going to be 2 squared. And since each thing in here corresponds to one of these, we know the number of things in here is also 2 squared. And so we have 2 times 2 squared, which is 2 cubed. That's the total number of subsets here. So that's the application for the case n equals 2. But this is just thinking about that in more general term, where you have, you know, n elements here, and 2 to the n, 2 to the n, add them together, you get 2 to the n plus 1. We will come back and prove this in a variety of ways this quarter. We already talked about it in set theory. When we looked at representations of sets in binary, we saw that, you know, every binary string of n bits corresponds to a subset of a set containing n things, and there's 2 to the n bit strings of n bits length, so there's 2 to the n subsets. And we'll keep coming back to this and looking at different ways to see this property of power sets. So this is just another presentation of that. But it's a lot more abstract and kind of touchy-feely than some of these other things we've proven. All right, so let's go.
What page has the last part of that proof?
This one. So we can go from here to an even stranger application of induction. This is something called an odd pi fight. And the idea is, you know, it's the last day of class, and everybody wants to sort of like spend their extra energy, and so you're going to have a pie fight in class. And so as you walk into the classroom, the teacher hands you a pie. Pick your favorite pie, chocolate cream, banana cream, whatever. And you're going to go into class and you get to throw this pie at somebody. All right. And the way that this pie fight is set up, you're going to walk into a room and you're going to stand in one spot. And so, you know, here's where some people are standing. And each person holds a pie in their hand. And when the whistle blows, you throw the pie at whoever is standing closest to you. All right? And the question is, does everybody get hit with a pie, or is it possible that somebody doesn't? Right? So is there a survivor of the pie fight? And to make this unambiguous, we're going to put one requirement on this, which is no two people can be the same distance from as any other two people. In other words, C can't be exactly the same distance from both B and D. So if this person happened to be exactly 2 feet from both of these people, we want them to move a little bit one way or another. So in this case, you know, A would probably throw their pie here, and E would throw their pie here, and C would throw their pie there, and D would throw their pie there, and B would probably throw their pie there, and B would not get hit by a pie. But, you know, if A was down here, A might throw their pie at B, but E would throw their pie at A, and E would end up surviving. But on the other hand, if we had 4 people in the room, they could be situated like this. And now A and B would throw pies at each other. C and D would throw pies at each other. Everybody got hit by a pie. Alright, so here's a theorem. The theorem is that under these rules for a pie fight, if you have an odd number of people, there's always a survivor. Alright, so theorem. In a pie fight of n people, if n is odd, someone survives. Alright, and this is going to be a super kind of intuitive hand-wavy proof. So we'll make a family of propositions. Let P of n be the proposition. Someone survives. An n pie fight. And we want to prove P of n for all odd n bigger than or equal to 3. We won't deal with the case where there's just one person because you're not allowed to throw the pie at yourself. Alright, so we're going to prove this for n bigger than or equal to 3 and odd. So what's the base case look like? P of 3. 3 people go into a room and they do this pie fight. And the distances between people are unique. Right? If 2 people are a distance x apart, there's no other 2 people who are also exactly x apart. So let me just sort of draw my 3 people. And I'm going to say pick the 2 people who are closest to each other. Now how would I do that? Well, I would list the distance between every pair of people, A to B, A to C, B to C, B to A, C to A, C to B. Right? And those distances are unique, so there's a smallest element in that. So I can find the 2 people who are closest to each other. And let's suppose that that's A and B. Let's suppose C is like further away. Alright. We can run this pie fight sequentially. They don't all have to throw their pies at the same time. So we can start off and we can say, okay, the 2 people who are closest to each other, throw your pies. And we know they're going to throw their pies at each other. And now neither of them has a pie that they can throw. C has not taken part in this yet. C is holding a pie, and they will either throw their pie at A or at B. But in either case, nobody throws a pie at C. C is a survivor. So P of 3 is true. So the more interesting part is the inductive step. So let's prove P of n implies P of n plus 2. Right, and I'm inducting by 2's here, but the idea is if I know P of n is true for 3, and I know P of n implies P of n plus 2, P of 3 tells me P of 5 is true. And if P of 5 is true, that tells me P of 7 is true. And if P of 7 is true, that tells me P of 9 is true. And I'm inducting up by odd numbers here. So I can prove this by proving this base case P of 3 and proving this slightly different inductive step. So we're going to prove P of n implies P of n plus 2. Alright, so picture a room with n plus 2 people in it. So I'm going to call these person 1, person 2, person 3, person n plus 1, and person n plus 2. And I don't know where they're standing in the room. I'm just kind of drawing them so that we can look at them. Alright, so again I'm going to say pick the 2 people closest to each other. And distances are unique, so there's always 2 people who are closest to each other. And I'm going to call those 2 people person n plus 1 and person n plus 2. That's just my names for them. So whoever's closest, I'm going to put a post-it note on their shirt and say you're person n plus 1, you're person n plus 2. And the other n people, I'll just put post-it notes p1 through pn. Alright, and we're going to let these 2 people throw their pies first. So again, since the person closest to this is this person, they're going to throw their pie there. And the person closest to n plus 2 is n plus 1, they're going to throw their pie right there. And now these people no longer have any pies to throw. Alright, so now let's see what happens with the rest of the pie fight. And there's 2 possibilities. Possibility 1. Some other person between person 1 and person n. So for some other person from person 1 through person n, their closest person is either pn plus 1 or pn plus 2. In other words, it's possible that of these remaining people in the room, the closest person to one of them is one of these 2. Right? Could happen. Could be someone standing right here really close to this, but not quite as close as these 2 were. If that's the case, then that person's going to throw their pie at one of these 2 people. Alright, so they throw their pie. And now, take a look at what's going on in the room. So now in the room, we have n people, we have n survivors, right? Because in that case, the only people who have been hit by pies are these 2 people. So we have n people who have not been hit by a pie, but how many pies do we have left? We only have n minus 1 pies, because this person just threw their pie at one of these 2. Well, if you have a room with n people and there's only n minus 1 of them who have pies in their hand, there's going to be at least one person who doesn't get hit, because you got more people than you have pies. And so someone survives. So that's one possibility. The second possibility is that this is not the case. If you look at all these people, for none of those people are one of these the closest person in the room. In other words, these n people are all going to throw their pies at each other. None of them are going to throw their pies at either of these 2. Well, if that's the case, we've got an n pie fight. We've got n people holding n pies, and guess what? We're assuming p of n is true, which means somebody survives that pie fight. And so since p of n, someone survives. And those are the only 2 possibilities. So if somebody from here throws their pie at one of these people, we'll have a survivor. If nobody from here throws their pie at these people, we'll still have a survivor. And so in either case, someone survives, and so p of n plus 2 is true. And that's enough using mathematical induction to prove p of n is true for all odd n. Alright, so that's a proof that personally I don't think I would ever come up with on my own. I read that when I was putting together lectures, and it seems really clever to me, but it's not something that I would think of, you know, of breaking off two people and working like that. Somebody very clever came up with that. Um,
That seems just like when you were shown the squares and you know, the 512 squares,
mm-hmm.
and then you take care of the three that are all identical prior, and
Mm-hmm.
this leaves you the smaller problem to the side broken up.
Yeah. And there's
So this could still be true for even, but it's not guaranteed to be true, which
Right.
is why it's not a proof.
right. Yeah. So for even, you might have a survivor, or you might end up with everybody getting hit. I think you can have survivors with even. So yeah.
Like I was thinking, like if you put everybody in a line linearly, and therefore even if it was even, at some point, and if everybody is spaced, let's say, you know, n plus 1 distance apart, the last person will be, their closest person will be the person before them, but the person before them's closest person will be the person before them.
Right.
And the first person's closest person will be the person number 2. So person number, so somebody's in here with 2 pies and one person's not.
Right. So yeah, you might have survivors with an even number, or you might not. So this, you know, the floor tiling question, you know, not something that it's clear how to come up with the proof, but the nice thing about proofs is you don't have to be clever enough to come up with the proof. You need to be skilled enough to understand the proof, right? This is why we do proofs, so that somebody who has the insight to see why something's true can present an argument, and then other people who haven't had that insight can look at the proof and say, "Oh, I see. Yes, that is true." Right? That's kind of the nature of the whole business of these proofs. But it's still this notion of you know, taking your problem, turning it into a statement about a family of propositions that you're trying to show is true, proving a base case, and then trying to prove some kind of inductive statement. And at some point in trying to prove, in this case, P of n plus 2, using P of n, right? And if you're not using P of n, you might be doing something wrong, or it might be a problem that could have been solved more simply than using a full-on inductive proof. But in all the problems we've done, at some point we have to go back and we have to use P of n in some way to show P of n plus 2 or n plus 1 or whatever. So that's kind of a fun problem.
Can you say more about how we were able to pick, you know, because before inductive reasoning says, well, you know, it has to be P of n, therefore P of n plus 1. No, now this time we're saying P of n plus 2. I mean, to some extent it's kind of, well, yeah, okay, sure, but I guess is there more to say about that? Is it like,
Yeah,
well,
I should be a little more.
Plus 1, I can say P of n plus 5, or, you know, some other arbitrary number.
I should be a little more precise about that. The whole idea of induction is being able to sort of climb the ladder, right? So if we want to prove some statement about multiples of 5, right? We could prove P of 5, and then if we can show P of 5 implies P of 10, we can get P of 10, and if we can show P of 10 implies P of 15, we've got P of 15. And if we did this enough, we could eventually, you know, prove P of 5,000, and so on. So we might do a base case like P of 5, and then show that P of n implies P of n plus 5, where n is a multiple of 5. And we could induct in that way. I think if we wanted to...
We
Go ahead.
kind of covered that by saying, you know, n is odd,
Mm-hmm.
and therefore intuitively we say, well, to keep an odd number odd, you must therefore add 2.
Right. Yeah, so we would need to actually say something like, you know, every odd number is writable as a smaller odd number plus 2. right, in order to actually assert that this inductive step gets us to every odd number. So if we want to prove it for some odd number, we need to know that when we subtract 2, we get a smaller odd number. So that needs to be made explicit.
Are we gonna have to do an induction like that on our next homework?
I don't know if I put questions like that. I don't think there's anything as kind of sort of freaky as the odd pie fight or the tiling of floors. I think the questions. Oh no, there's one good one in there. Yeah, I think they're all basically mathematical in nature. So it's similar to, adding successive integers and getting n times n plus 1 over 2, that kind of thing. And they'll be largely questions about, what is this kind of magic step in the middle where you add n plus 1 to n squared and you get such and such, right? And you want to try to figure those out, right? But your goal at the end of the homework is to have a clear understanding of induction. But struggling with some of these algebraic equations is part of that. So another question: why does this work? Why is this a true theorem? Why is it that if p of 1 is true and p of n implies p of n plus 1, that we can say p of n is always true? I mean, that is what mathematical induction is. It's this theorem. And that's what we're doing. We're proving a base case, we're proving an inductive step, and then we're just automatically saying, hey, therefore, all of these propositions are true. But why is that? Why does that work? And it's a really subtle kind of thing. And we can prove this by doing a proof by contradiction. And I'm not going to make this entirely rigorous because this gets into like foundations of integers and things like that. But here's the intuition for why this works. So suppose p of 1 is true, and suppose p of n implies p of n plus 1 for any n bigger than or equal to 1, and suppose p of some bad number b is false. So suppose this fails. Mathematical induction is broken. We've got p of 1, we've got p of n implies p of n, but suppose this is not a true statement. So the negation of this is there exists an integer n where p of n is false. Right? There's some p of b which is false, where b is bigger than or equal to 1. Alright, so here's what we do. Since all of the numbers that we're considering are positive integers, if we take all the numbers where this proposition fails, we can find the smallest such number. In other words, if this fails for 17, 56, and 8, I can pick the smallest of those numbers and say, hey, this fails for p of 8. So let's pick b to be the smallest integer bigger than or equal to 1 for which p of b is false. So we're going to find the first value of n for which p of n fails to be true. And we can find a contradiction really easily, right? So how do we find a contradiction? We know that B is bigger than 1 because P of 1 is true, so P of 1 is true, right? And so since B is the smallest number for which this is true, we know that P of B minus 1 is true because B minus 1 is smaller than B. But from our inductive step, we know that P of B minus 1 implies P of B. And therefore, we can use detachment, and that shows P of B is true, and that's a contradiction of P of B is false. So proving this is not too bad, other than being able to pick the smallest of all the values for which P of B is false. And that's a kind of subtle property of integers. And it's tied into something called well ordering, but it's a safe thing to do. The intuition of why induction works is this idea of using a chain rule, basically. If P of 1 implies P of 2, and P of 2 implies P of 3, and so on, and P of 999 implies P of 1000, I can chain all of those together and say P of 1 implies P of 1000, and my base case tells me P of 1, and I can use detachment and therefore say P of 1000. And I don't have to stop at 1000, I could stop at 1,000,000 or 1,000,000,000 or whatever. All right, other questions?
So on that, past the P of B, where we have the P of B minus 1, therefore P of B, that's because P of N implies P of N plus 1 is true, and I mean in that step are we basically saying that true implies false, and there's our contradiction, or is it the next step we say, well, therefore P of B is true? We've already said that P of B is false up above.
Yeah, so this is just applying our inductive hypothesis, which we've said is true, to B minus 1, which tells us P of B. That's still not a contradiction until we take this and this, put them together with detachment to get this, and that contradicts our assumption that P of B is false. So that's where the contradiction comes in. All right. So one more example of induction, and so this is the famous proof that all horses are brown. So anytime you see a horse, it's going to be brown, guaranteed. There's no white horses, there's no spotted horses, there's no black horses. All horses are brown. And we're going to prove this using induction. And if you know anything about horses, there's got to be something wrong with our proof, because horses come in all sorts of colors. But nonetheless, let's do a proof based on mathematical induction that all horses are the same color. In particular, they're brown. All right, so let's prove all horses are. Let's prove all horses are the same color. And since I've seen a brown horse, that's going to prove all horses are brown. So let's prove all horses are the same color. So let P of N be the proposition in a field containing N horses, all those horses are the same color as each other. So what we're actually going to prove is that in any finite collection of horses, all those horses are the same color. I guess if there's an infinite number of horses, this might not work. But, you know, if you take 100 horses and you put them all in a field, they're all going to be the same color. So that's what P of 100 says. Alright, so how do we prove this? Let's start with a base case. P of 1. P of 1 says if you have a field containing a single horse, every horse in that field is the same color. Is that true? Right, if that horse is brown, every horse in the field is brown. If that horse is red, every horse in the field is red. If that horse is rainbow colored, every horse in that field is rainbow colored. So it doesn't matter what color the horse is. If you have a single horse in a field, you can make a statement, every horse in this field is the same color. And that's absolutely true if you only have one horse. So the base case is easy. The inductive step, we need to prove P of n implies P of n plus 1. So we're going to have a field containing n plus 1 horses. And I'm going to call them horse 1, horse 2, horse 3, horse n plus 1. They're going to be standing in a row because that's what they like to do. Alright, so they're hanging out in a field. And I put them side by side so I can talk about them. And the claim is that all of these horses are the same color as each other. And here's how we prove it. We take these horses and first we consider this subset of n horses. Well, since we're assuming P of n, and here's a collection of n horses, all of these horses are the same color. So these are all the same color. I'll just call it color C. Brown, red, black, whatever. Now I make a second collection of horses containing these n horses. And this is a collection of n horses, and P of n says any collection of n horses are all the same color. These are all the same color. Let me call it C2. But, you know, horse 2, for example, is in both of these collections. Since horse 2 is color C and also color C2, C and C2 must be the same. And so all n plus 1 horses are all color C, which is the same as color C2. And so as long as we know that n horses are all the same color, it's easy to show that n plus 1 horses are the same color. And therefore P of n for all n bigger than or equal to 1. So there you go. Pick 1,000 horses, put them in a field, they're all going to be the same color. So the question is, what's wrong with this proof? Because we know horses come in different colors.
It's only proving information based on a finite set and not an infinite set.
Well, this is true, it's only proving it on a finite set, but that's all we ever really do with induction, right? P of n is always a finite number. The statement of our propositions is, for example, P of n is true for all n bigger than or equal to 1. Doesn't say it's ever true for an infinite n, right? Infinity is not an integer, but it says for any integer, no matter how big that integer is, this proposition is true. And so we're showing no matter how many horses, as long as it's a finite number, all those horses are going to be the same color as each other. So that's actually legit. But there is still a problem somewhere, hopefully.
Well, we're only proving this is true for the base case, right?
Well, we proved it for the base case, which is one horse, but then we did this inductive step. And we showed if you have n plus 1 horses, well, each subset of n horses contains horses that are all the same color. And since, you know, these horses belong to both of those subsets, all n plus 1 horses have to be the same color. And there's like no math anywhere in sight here, right? This is purely like an intuitive, hand-wavy version of an inductive problem. But there is a logic error somewhere. This is also one I had to.
Assuming that P of n is true.
We are assuming P of n is true. That's how we go about proving this inductive step. We're not proving P of n is true, but we're saying if P of n is true, can we show P of n plus 1 is true? So yeah, we're definitely assuming P of n. That's allowed. What I'm proving in this argument is this conditional statement. And then that plus the base case lets us use mathematical induction to claim this. And the base case is fine. That's not where the problem is. The problem is somewhere in the inductive step.
I guess
We're assuming that color is what increments the like the next variable in the set, like the color of the horse isn't dependent on. I'm sorry, I'm losing my train of thought already.
I thought I knew where you were going. Somebody else started to say something?
yeah, I was gonna say in our when we did the C2, we were kind of assuming that last n plus 1 is the same color as all those other ones.
Which it is, because this, if we take all the horses except the first, that's a collection of n horses, and P of n is true, so all of these horses have to have the same color as each other.
It seems like it would be a problem with the collection, because we all know there are horses of different colors, but in this set they all happen to be brown, right?
Yeah. But they don't just happen to be brown or, you know, all the same color. They're the same color because we're assuming P of n. And this is sort of the point of this. When we do an inductive proof, we never actually know if P of n is true. It's always an assumption. If this is true, can we prove that? And we're never actually going to prove P of n is true until we've got a base case in an inductive step. But we can suppose P of n is true. We can suppose, you know, I can flap my arms and fly, and show if that's true. Then I can get to Portland in less than 5 minutes. Right?
That's why it's not immediately apparent when you do a mathematical proof of this, because, you know, 2 equals 2 is pretty straightforward.
Mm-hmm.
But if you say prove P of n 0 equals 2, and then you just moved on to the inductive step, then you were treating it like 0 equals 2 is true. You could just move on to the inductive step.
Right. What stops you from getting into trouble there, though, is that you need to have a base case. So, for example, you could try to prove n equals n plus 1 for all n. And you can prove the inductive step really easily, but you don't have a base case. But in this case, we do have a base case. We know that if we have a single horse, it's the same color as itself, basically. So send me an attendance note. Let's take like a 3-minute break and think about this a little more, and I'll come back and tell you the problem with the proof if you haven't come up with it. But let's do like a 3-minute break.
want to go inside?
All right, what do you think?
Is it because we're removing the base case from the second group comparison?
You might be onto something.
Is
We broke the chain and the ladder.
Yeah. So here's the trick.
You removed your rung. You removed your bottom rung. If you remove P of 1, how do you know that you get to P of 2?
Yeah, we actually broke the second rung, I think. So this little hand wavy proof here, I slipped something by in here. We said if you have n plus 1 horses, we can find n horses here, and we can find n horses here. And since there's horses that belong to both of those subsets, all the horses have to have the same color. But there's one case where this doesn't work, and that's the case where n equals 2. And if n equals 2, here's what we have. 2 horses, and I break them into 2 subsets of 1 horse each. So here's a subset of 1 horse. Here's a subset of 1 horse. There's no overlap. There's no horse in common to both of these subsets. So P of 1 tells me all of these horses are the same color. P of 1 tells me all of these horses are the same color. But this business of saying, you know, since there's horses that belong to both sets, well, that doesn't apply here. There's no horse that belongs to both.
so the groups that you circled or that you squared separately were kind of illegally lumped together
Yeah,
since they didn't build on the.
there's only overlap if you have at least 3 horses. So this is only true when n is bigger than or equal to 2. In other words, when you have at least h1, h2, and h3. So for this to work as part of an inductive proof, I need a base case that's at least P of 2. And there's no such base case. There's no way I can prove that if I take any 2 horses, they're going to be the same color as each other. That doesn't happen. So I don't actually have a base case that can be put together with this inductive step, because this inductive step only works for n bigger than or equal to 2. Now, if it was true that any pair of horses are the same color, you can see immediately that all horses have to be the same color. If any two horses are brown, every horse in the world has to be brown. Because I can take one of those brown horses, I can pair it with, you know, some random horse. There's two horses that have to be the same color. Since this one's brown, this new horse has to be brown. So if you could prove P of 2, you could prove this theorem and it would be absolutely true. But P of 2 is just not true. So this is an illustration where the base case is really, really important. And when you're working through the inductive step, make sure that you remember what the conditions are on this n that you're inducting on. And we can see simpler examples of this. So for example, prove n equals n plus 1 for all n bigger than or equal to 1. Well, let P of n be the proposition n equals n plus 1. Can I prove P of n implies P of n plus 1? Absolutely. This is a true statement. And it's trivial to prove. P of n is the hypothesis. N equals n plus 1, that's the definition of P of n. Add 1 to both sides, n plus 1 equals n plus 1 plus 1 equals n plus 2. That's algebra. Well, if n plus 1 equals n plus 1 plus 1, that's P of n plus 1. So this is absolutely true. But we don't have a base case that we can put with this. P of 1 is not true because P of 1 says 1 equals 2, and that's not true. P of 0 says 0 equals 1, that's not true. So even though we can prove this inductive step, if we don't have a base case, we have no first rung of the ladder. We have a ladder, you know, floating in the air that we can't get to. And so there's no way to get to any of the rungs. So that can be kind of subtle, right? And we usually don't run into this, but if you encounter sometimes a paradox, right, or something that looks like a paradox using an inductive proof, go back, look at your base case, see if there's some assumptions that are being made that that shouldn't have been made, and so on. All right, questions about any of that? This is only our first pass through induction. We'll encounter this at different points throughout this course, and then we'll use this in CSE215 in winter.
So just kind of going back to the horse one,
Yeah.
you're saying that since we can't prove it from 2 to 2, and that's because the n, or you're saying like because of the stipulation on that, where n is any two horses, or in that case any two horses, and since we can't prove it for any two horses, then it's false.
Right.
So in general, like, I guess is there something, are we saying something generally about that, like where from it's always like any two, or is that kind of what the n is always saying, or that was just in that particular case?
So this was just in this particular case, and it was because the proof of this inductive step very subtly used the idea that n was at least 2. And this proof of this inductive step does not work if n is equal to 1. Because if n is equal to 1, this picture actually looks like this, and there's no overlap between those two subsets. So in this proof, I without saying so, I use the assumption that n was at least 2, which means my base case has to apply for n equals 2, and it doesn't. Now most of the proofs we've done, we've either been careful or lucky that the thing that we did to prove the inductive step wasn't dependent on some different value of n, right? Usually we prove these things for n bigger than or equal to 1. Our base case is 1, and even if n is equal to 1, our demonstration of the inductive step has been valid. But this is one where n has to actually be at least 2. And it's the same thing that goes wrong here, right? In this case, there is no base case. There is no particular value of p of n for which p of n is true. In the horse case, p of n does imply p of n plus 1 as long as n is at least 2, but p of 2 doesn't happen to be true. In this case, p of n is always false. And so this doesn't prove anything except, you know, if 1 was equal to 2, then 2 would be equal to 3. So we'll let that percolate in our brains for a few weeks. And we'll change gears and move into our next unit, which is counting. So this is at least in the beginning a fair bit easier to talk about and think about than induction. So what is counting? 1, 2, 3, 4, 5. Right? Sesame Street, the count, all of that stuff. Well, a little bit easier, yeah. But with this, you know, seemingly simple notion of counting, we can do a lot of powerful things. We can analyze a lot of situations and answer some fairly involved questions. And this is going to take us into permutations and combinations, finding the number of ways to do some things. It's going to take us into a revisiting of some of the things we did in set theory, where we, you know, this many people are in school and this many take art and this many take math, and how many of them, you know, wear mismatched socks or something. We'll look at how to do things like that, and it will end up with some fairly surprising and beautiful results when we talk about Pascal's triangle, which is related to combinations and lots of weird properties around there. But let's start with just the idea of counting, and the first notion is something called the product rule. And this is something we might understand intuitively, but let's make it sort of formal. So the idea of the product rule is, given a procedure, so some procedure P that you're trying to do, given a procedure P which can be accomplished as a succession of tasks so some procedure which is a succession of two tasks, T1 and T2. So P might be the procedure for getting dressed. And the first task is to pick a shirt, and the second task is to pick a pair of pants. Right? So that's the procedure you're trying to do, and if you can split it into two tasks, T1 and T2. Okay, that's our setup. So given this, if T1 can be done N1 different ways, and if T2 can be done N2 different ways, then P can be done N1 times N2 different ways. That's the product rule. So you have some procedure that you can accomplish by performing two subtasks, T1 and T2, in order. If there's n1 ways to do T1, n2 ways to do T2, there's n1 times n2 ways to do that original procedure. So for example, pick a jacket. So dress for outdoors. That's our procedure. And I'm going to say this is doable by a succession of two tasks. Task 1 is pick a hat, and task 2 is pick a coat. I know people don't wear hats anymore, but let's pretend. So pick a hat and pick a coat. Alright, if you have 5 hats that you can choose from, and you have 3 coats that you can choose from, there are a total of 15 ways that you can dress to go outdoors. Right? You could do hat 1 with coat 1, hat 1 with coat 2, hat 1 with coat 3. There's 3 ways. Hat 2 with coat 1, 2, or 3, there's another 3 ways. Hat 3 with coat 1, 2, or 3, there's another 3. You can do that a total of 15 different ways. That's the product rule. And that's really all there is to it. So if you have a procedure that can be done as a succession of 2 tasks, the number of ways to do the procedure is the product of the number of ways to do each task. Does that make sense?
Did you use it to find like the number of permutations or something?
We will use this eventually to find number of permutations and number of combinations. And playing cards and picking balls out of bags and all kinds of stuff.
Cool, because I've always kind of wanted to know the math behind a Rubik's Cube and how they figure out how many permutations it has.
Oh, that's a hairy question for sure. I don't know if we'll cover all of that. Yeah, we might. Trick with a Rubik's Cube is that, you know, if you do a certain number of things, you might come back to where you started at some point. So that's going to be more complex to analyze. But yeah, we'll get into some of that.
Oh, the moves aren't independent.
Right. So just as a parting teaser on all of this, suppose we have a procedure that can be done as a succession of 3 tasks, where each task can be done n1, n2, n3 ways. Do you believe that the number of ways to do the procedure is the product of those 3 numbers? In other words, does this generalize to 3 tasks? What do you think?
I think we could prove that with induction.
Hey!
Q implies Pn plus Pn implies Pn plus 1.
Right? So we could think of this as a task, and our product rule says, hey, since this task can be done as T2 followed by T3, this one task can be done n2 times n3 ways. This task can be done n1 ways, and our product rule says the total number of ways is this times that. That's that. So we can prove this for 3 given it's true for 2. And then if we know it's true for 3 ways and we have a 4th task, can we prove that the total number of ways is this? Well, yeah, same thing. We could say this is one task, this is another task. Since we know this is true for 3 tasks, then our product rule says this times n4, that's the number of ways to do our whole procedure. And to generalize that and say for, you know, k tasks, it would just be the product of n1 through nk. That's where we can throw mathematical induction at it. So we won't have to do that. We'll just take this as given that if you can split your procedure into k tasks, t1 through tk, and each of those can be done n1, n2, nk ways, the product of all of those gives you the number of ways you can do your procedure. Alright, so we'll start from here on Friday. Send me an attendance note. We'll start from here Friday. We'll look at how you use the product rule for certain examples, and then we'll move on to another rule called the sum rule, which is similar. And then we'll look at combinations of those, we'll look at subtraction, and then we'll start talking about pigeonholes. So you're good to go after an attendance note. Have a great afternoon. I will see you tomorrow if you're in 224. Otherwise, I'll see you Friday.